September 15, 1940. The skies over London. Flight Lieutenant James Nicholson pushed his Hawker Hurricane into a steep dive, pursuing a German Messerschmitt Bf 109 that had just strafed a formation of British bombers. The German pilot, seeing the Hurricane diving after him, pushed his own aircraft into a vertical dive. A maneuver that Luftwaffe pilots had learned gave them decisive advantage over British fighters. Nicholson followed, his thumb hovering over the firing button, waiting for the German aircraft to enter his gun sight. Then disaster struck. The Rolls-Royce Merlin engine powering Nicholson's Hurricane coughed once, sputtered, and died completely. The propeller windmilled uselessly as the aircraft, suddenly without power, became a falling brick rather than a controlled diving fighter. Nicholson pulled back on the stick, trying to level out and restart the engine, but the Hurricane continued its uncontrolled descent toward the London streets below. The German Bf 109, its fuel-injected Daimler-Benz engine continuing to run perfectly through the dive, pulled out smoothly and disappeared into the clouds. Nicholson fought desperately with his dead aircraft, pumping the throttle, working the fuel mixture controls, trying everything he knew to restart the engine that had quit for no apparent reason. At 3,000 feet, the Merlin suddenly coughed back to life, fuel finally reaching the carburetor again as positive gravity returned to normal levels. Nicholson pulled out of the dive with barely 1,000 feet of altitude remaining, his Hurricane vibrating from the stress of the emergency recovery. He climbed back toward his squadron's position, alive but furious. The German pilot had escaped because British fighters had a fatal flaw that cost lives and battles every single day. The problem that nearly killed James Nicholson was killing British pilots across the Channel and over Britain throughout the summer and fall of 1940. It was not enemy superiority or pilot skill or tactical doctrine. It was engineering, specifically the carburetor design in the Rolls-Royce Merlin engine that powered both the Supermarine Spitfire and the Hawker Hurricane, the two fighters on which Britain's survival depended during the Battle of Britain. The Merlin engine was a magnificent piece of engineering in almost every respect. It produced over 1,000 horsepower from a V12 configuration, providing speed and climb rate that made Spitfires and Hurricanes competitive with German fighters. It was reliable under normal operating conditions, with failure rates far lower than many contemporary engines. It could be manufactured in quantity by British industry despite wartime constraints. It had been developed over years by Rolls-Royce engineers who understood aircraft engine design as well as anyone in the world. But the Merlin had one catastrophic weakness that stemmed from a design choice made years before the war, when no one anticipated the kind of combat maneuvering that would be required in fighter-versus-fighter dogfights. The Merlin used a float carburetor to mix fuel and air for combustion. This was standard technology in 1930s aircraft engines, proven and reliable for normal flight operations. The float carburetor worked through elegant simplicity. Fuel from the aircraft's tanks flowed into a chamber containing a float mechanism similar to what controls water level in a toilet tank. As fuel filled the chamber, the float rose, eventually closing a valve that stopped additional fuel from entering. When the engine consumed fuel, the level dropped. The float descended. The valve opened, and more fuel entered to maintain proper level. The system worked perfectly as long as the aircraft maintained relatively constant gravity forces. In level flight, in gentle climbs, in coordinated turns, the float carburetor maintained proper fuel-air mixture, and the engine ran smoothly. But when a pilot pushed the aircraft into a dive or performed other maneuvers creating negative gravity forces, the float carburetor experienced catastrophic problems. Under negative gravity, the fuel in the carburetor float chamber was pushed upward rather than sitting at the bottom of the chamber as gravity normally dictated. The float, designed to rise and fall based on fuel level under normal gravity, was suddenly pushed upward by fuel that was being forced toward the top of the chamber by negative G-forces. When the float rose, it closed the fuel valve, cutting off fuel supply to the engine. Simultaneously, the fuel feed tubes that normally drew fuel from the bottom of the chamber were suddenly drawing from the top of the chamber, where air rather than fuel accumulated under negative G conditions. The engine received a mixture that was too lean, mostly air with insufficient fuel. The Merlin would cough, sputter, and often quit completely within seconds of entering negative G maneuvers. The engine failure was temporary. Once the aircraft returned to positive G flight, gravity forced fuel back to the bottom of the chamber. The float returned to proper position. Fuel flow resumed, and the engine would restart. But those seconds when the engine quit could be fatal in combat. A pilot pursuing an enemy aircraft into a dive would lose his engine and lose his target. A pilot trying to escape an enemy on his tail by diving away would lose power and become helpless. A pilot maneuvering violently to avoid enemy fire could find his engine quitting at the worst possible moment. German Messerschmitt Bf-109 fighters did not suffer this problem. Their Daimler-Benz engines used fuel injection rather than carburetors. Fuel injection systems pumped fuel directly into the cylinders under mechanical pressure, completely independent of gravity. A Bf-109 could perform any maneuver in any attitude with any G-loading, and the fuel injection system would continue delivering proper fuel mixture. German pilots learned quickly that diving away from pursuing Spitfires or Hurricanes would cause the British fighters to lose power, giving the German pilot free escape. The tactical advantage this provided was enormous and cost British lives daily throughout the Battle of Britain. RAF pilots knew about the problem. They experienced it in every dogfight. They reported it in debriefing after debriefing. They developed tactical workarounds, learning to half-roll before diving so that negative G became positive G. But this maneuver took precious seconds during which an enemy could escape or could gain advantage. They learned to avoid certain maneuvers entirely, limiting their tactical options. They accepted that German fighters had inherent advantage in certain situations. But knowing about the problem and accepting limitations did not make the problem less deadly or less frustrating. British pilots were dying because their fighters' engines quit during combat maneuvers. Everyone from squadron commanders to Air Ministry officials knew the problem existed. The question was whether anyone could fix it. Rolls-Royce engineers had been working on the carburetor problem since early reports from France during the Battle of France in May 1940. They understood the technical cause. They recognized the tactical consequences. They explored various solutions, including complete redesign of the carburetor system or conversion to fuel injection similar to German engines. But every solution they examined required extensive engineering development, testing, certification, and most critically, time. Redesigning the Merlin's fuel system would require months of engineering work. Building prototype fuel injection systems would require manufacturing capacity that was already stretched, producing engines for the fighters desperately needed to defend Britain. Testing new fuel systems would require pulling aircraft from operational squadrons for evaluation flights. Certifying new designs would require bureaucratic processes and safety reviews. The timeline for any comprehensive solution extended into 1941 or beyond. Britain did not have months to wait for engineered solutions. The Battle of Britain was happening now, in summer and fall of 1940. German bombers were attacking British cities daily. Luftwaffe fighters were engaging RAF fighters in dogfights that would determine whether Germany could achieve air superiority necessary for invasion of Britain. Every day that the carburetor problem remained unsolved was a day when British pilots fought with one hand tied behind their backs, unable to fully exploit their aircraft's capabilities because the engine would quit if they maneuvered too aggressively. Into this desperate technical and tactical situation stepped Beatrice Shilling, known universally as Tilly, an engineer at the Royal Aircraft Establishment at Farnborough. Tilly Shilling was 33 years old in 1940, a woman working in an engineering field almost entirely dominated by men, someone who had fought every step of her career for recognition and opportunity that male colleagues received automatically. She had earned a degree in electrical engineering from Manchester University in 1932, one of very few women in Britain to achieve university education in engineering during that era. She had faced discrimination and dismissal throughout her education and early career. Male professors had questioned whether women possessed the intellectual capacity for engineering. Male employers had refused to consider her for positions because they assumed women were not serious about engineering careers. Male colleagues had treated her as novelty or as token rather than as professional equal. Tilly had persisted through determination that bordered on obsessive and through ability that exceeded most of her male peers. By 1940, she worked at the Royal Aircraft Establishment, one of Britain's primary centres for aeronautical research, where she focused on engine performance and specifically on problems affecting combat aircraft. She rode a motorcycle to work daily, a Norton that she had personally modified and tuned to achieve performance far beyond factory specifications. She raced motorcycles competitively in her spare time, competing against men and frequently winning. She understood engines at visceral level that combined theoretical knowledge with practical mechanical intuition. She knew how engines breathed, how fuel and air mixed, how combustion occurred, how mechanical components translated chemical energy into rotational power. When reports about the Merlin carburetor problem reached Farnborough in mid-1940, Tilly recognized immediately that the comprehensive solutions being explored by Rolls-Royce engineers, while ultimately correct and necessary, would arrive too late to affect the current battle. Britain needed a solution now, not in 6 months or a year. The solution did not need to be perfect. It needed to be good enough to allow pilots to dive without losing their engines. It needed to be simple enough to implement quickly. It needed to require minimal modification to existing engines so that it could be retrofitted to fighters already in service. Tilly began analyzing the carburetor problem not as comprehensive engineering challenge requiring complete redesign, but as immediate tactical problem requiring expedient fix. The core issue was that negative G-forces caused fuel to flood the carburetor, pushing too much fuel through the system while simultaneously exposing the fuel feed to air rather than to liquid fuel. The flooding caused the float to rise and close the fuel valve, while the air exposure caused fuel starvation. What if, Tilly thought, the fuel flow could be restricted just enough to prevent flooding during negative G maneuvers while still allowing sufficient flow for normal engine operation? A restriction would limit how much fuel could enter the carburetor chamber regardless of G-forces. It would prevent the float from rising too high and closing the valve completely. It would maintain some fuel flow even under negative G conditions, perhaps enough to keep the engine running even if not at full power. The solution Tilly conceived was almost insultingly simple. A metal disc with a precisely sized hole drilled through its center, installed in the fuel line between the fuel pump and the carburetor. The disc would restrict total fuel flow to a calculated maximum rate. Under normal positive G conditions, the restriction would have minimal effect because the engine was not trying to consume more fuel than the restricted flow provided. Under negative G conditions, the restriction would prevent excessive fuel from flooding the carburetor, maintaining more stable fuel level and preventing complete engine failure. The device would require no modification to the engine itself. It would install in the fuel line using standard fittings. It could be manufactured by any machine shop capable of drilling a precise hole in a metal disc. It could be installed in minutes by mechanics with basic tools. It could be retrofitted to every Merlin engine in service within weeks if it worked. The challenge was calculating the exact size of the restrictor hole. Too large, and it would not prevent flooding. Too small, and it would starve the engine of fuel even under normal conditions, reducing power and potentially causing engine failure during high-power operations like takeoff or combat. Tilly needed to determine the optimal restriction that balanced preventing negative G fuel flooding against maintaining adequate flow for all normal operations. This required understanding exact fuel flow rates under various operating conditions, understanding how much restriction the engine could tolerate, understanding the dynamics of fuel behavior under different G loadings. Tilly spent weeks in late summer 1940 calculating, measuring, and testing. She obtained detailed specifications for Merlin fuel consumption rates at different power settings. She measured actual fuel flow through carburetors under laboratory conditions. She calculated how much restriction would be required to prevent flooding based on the volume of the carburetor float chamber and the rate at which negative G forces would push fuel upward. She consulted with Rolls-Royce engineers who provided data about fuel system pressures and flow rates. She performed test installations on ground-running engines, measuring how different restrictor sizes affected fuel pressure, mixture ratios, and engine performance. Her calculations indicated that a restrictor with an orifice approximately 0.06 inches in diameter, installed in the fuel line to each carburetor, would provide optimal balance. The restriction would limit fuel flow enough to prevent catastrophic flooding during negative G maneuvers while allowing sufficient flow for full power operation under positive G conditions. Tilly fabricated prototype restrictors, simple brass discs about 1 inch in diameter with precisely drilled holes. She specified that the hole edges must be smooth and deburred to prevent turbulence in fuel flow. She specified the exact position in the fuel line where the restrictor should be installed to achieve optimal effect. She prepared installation instructions simple enough that squadron mechanics could perform the modification without specialized training or tools. Testing the restrictor required convincing skeptical officials that a woman engineer's simple disc with a hole in it could solve a problem that Rolls-Royce's best engineers had been unable to fix with comprehensive redesign efforts. Tilly faced the same discrimination she had encountered throughout her career, magnified by wartime urgency and by the inherent conservatism of military and engineering bureaucracies that resisted unconventional solutions from unconventional sources. Male engineers questioned whether Tilly's calculations were correct, demanding that she explain her mathematics in detail that male engineers would not have been required to provide. Officials questioned whether such a simple solution could really work when comprehensive redesigns had been deemed necessary. Test pilots, accustomed to dealing with male engineers, were skeptical about entrusting their lives to a modification developed by a woman. Tilly persisted through force of personality and through the undeniable correctness of her technical analysis. She explained her calculations clearly and defended them against every objection. She pointed out that her solution required minimal resources and minimal time to test, that even if it proved inadequate, it would not prevent continued work on comprehensive solutions, that the potential benefit justified the small investment in testing. She emphasized that every day without a solution was costing pilots' lives and was giving German fighters tactical advantage that Britain could not afford. In October 1940, RAF test pilots at Farnborough agreed to evaluate aircraft fitted with Tilly's restrictors. The tests involved installing the restrictors in Hurricanes and Spitfires, then performing aggressive combat maneuvers, including steep dives and negative G maneuvers that would normally cause engine failure. The test pilots approached the evaluation with skepticism born of experience. They had flown these aircraft for months. They knew exactly how the engines would respond to negative G maneuvers, which was to quit immediately. They doubted that a simple washer in the fuel line would make any difference. The first test flight occurred on a clear October morning. The test pilot, squadron leader J.E. Johnson, climbed a Hurricane to 15,000 feet, leveled off, then pushed the nose down into a steep dive while simultaneously applying forward pressure on the stick to create negative G forces. Every pilot who had performed this maneuver in a Hurricane or Spitfire knew what would happen next. The Merlin engine would cough, sputter, and quit. Johnson waited for the familiar sensation of the engine dying. It did not come. The Merlin continued running throughout the dive and through the negative G maneuver. The engine's sound changed, becoming slightly rougher, and power decreased somewhat, but the engine did not quit. Johnson pulled out of the dive, climbed back to altitude, and repeated the test. Again, the engine continued running through negative G maneuvers that would normally have caused immediate failure. He performed the test repeatedly, each time experiencing the same result. The engine ran where it should have quit. Johnson landed and reported to Tilley and the other engineers observing the test. His assessment was direct and enthusiastic. The restrictor worked. The engine no longer quit during negative G maneuvers. Power decreased somewhat during negative G flight, but remained adequate for maneuvering. The pilot could now dive on enemy aircraft without fear of engine failure. The tactical advantage that German fighters had exploited for months was eliminated. Tilley's solution worked exactly as her calculations had predicted. Additional test flights over the following days confirmed Johnson's assessment. Every test pilot reported the same experience. Engines fitted with the restrictors continued running through maneuvers that would have caused certain failure without the modification. The power loss during negative G flight was noticeable but acceptable. Pilots could perform all necessary combat maneuvers without the engine failures that had plagued them throughout the Battle of Britain. The solution was everything Tilley had promised: effective, simple, quick to implement, and requiring minimal resources. The RAF designated the device officially as the RAE restrictor, named for the Royal Aircraft Establishment where it had been developed. Pilots immediately began calling it Miss Shilling's Orifice, a nickname that mixed admiration for the device's effectiveness with the innuendo that was common in military culture. The name stuck and became the device's universal designation among the pilots whose lives it saved. Production of Miss Shilling's Orifice began immediately in October 1940. Machine shops across Britain manufactured the simple brass discs by the thousands. The restrictor's simple design meant that any competent machinist could produce it to specification with basic equipment. No specialized tooling was required. No complex assembly was necessary. A machine shop could produce hundreds of restrictors per day. Installation began across RAF Fighter Command in November 1940, as restrictors were distributed to squadrons and installed by squadron mechanics in every Hurricane and Spitfire. The installation required approximately 30 minutes per aircraft. Mechanics simply removed a section of fuel line, installed the restrictor using standard fittings, and reconnected the fuel line. No engine disassembly was required. No recalibration was necessary. No complex testing was needed beyond normal engine run-up checks. By December 1940, most frontline fighters in RAF Fighter Command had been fitted with Miss Shilling's Orifice. Pilots reported immediate improvement in combat effectiveness. They could now pursue diving German aircraft without losing power. They could perform aggressive defensive maneuvers without fear of engine failure. They could exploit their aircraft's full aerobatic capability rather than flying within the constraints imposed by carburetor limitations. The psychological effect was as significant as the tactical benefit. Pilots who had spent months fighting with the knowledge that their engines would fail during certain maneuvers now fought with confidence that their aircraft would respond predictably to all control inputs. The impact on combat outcomes is difficult to quantify precisely because many factors affected Battle of Britain results, and because the restrictor was introduced during the battle's final phase when German strategy was already shifting away from daylight fighter operations. But pilot testimonies consistently emphasized that Miss Shilling's Orifice eliminated a significant tactical disadvantage that had cost lives and allowed German aircraft to escape situations where they should have been destroyed. German pilots noticed that British fighters were no longer losing power during dives, and reported this change to Luftwaffe intelligence, which correctly concluded that British engineers had solved the carburetor problem. The tactical advantage that Bf-109s had enjoyed through superior dive performance was neutralized. British and German fighters now fought on more equal terms with outcomes determined by pilot skill, tactical situation, and numerical advantage rather than by inherent technical superiority favoring one side. The restrictor remained standard equipment in Merlin-powered fighters throughout 1941 and into 1942, despite being explicitly designed as temporary expedient. Rolls-Royce continued development of comprehensive carburetor improvements and eventually introduced redesigned carburetors that solved the negative G problem through better engineering rather than through simple restriction. But the improved carburetors did not reach operational squadrons in significant numbers until mid-1942. For nearly 2 years, Miss Shilling's Orifice was the solution that kept Merlin engines running through combat maneuvers. The story of Miss Shilling's Orifice reveals multiple lessons about engineering, innovation, bureaucracy, and gender that extended far beyond its immediate tactical impact. First, it demonstrated that simple solutions to complex problems are possible when someone is willing to think outside conventional approaches. Rolls-Royce engineers working on the carburetor problem had focused on comprehensive redesigns because that was the proper engineering approach to solving fuel system issues. Their solutions would have been better in absolute terms than Tilley's simple restrictor. But their solutions required time that Britain did not have. Tilley's willingness to accept a good enough solution rather than insisting on the best possible solution produced results when results mattered most. Her engineering was not more sophisticated than Rolls-Royce's engineering. It was more pragmatic, more focused on immediate operational needs rather than on theoretical optimization. Second, the story demonstrated how bureaucratic and cultural barriers can prevent good ideas from receiving consideration. Tilley's solution was so simple that many engineers and officials assumed it could not work precisely because it was simple. Their mental models of engineering problem-solving assumed that difficult problems required complex solutions. A brass disc with a hole in it did not match their expectations of what an engineering solution should look like. Additionally, the solution came from a woman engineer at a time when women in engineering were rare and often not taken seriously. Tilley had to fight for her solution to receive fair testing, not because her analysis was wrong, but because her gender and her solution's simplicity created skepticism that a male engineer proposing a complex solution would not have faced. Third, the story demonstrated how wartime urgency can sometimes overcome peacetime barriers to innovation. In normal peacetime conditions, Tilley's unconventional solution proposed by a woman engineer would likely have been dismissed or would have been subjected to extensive review processes that would have delayed implementation indefinitely. But the Battle of Britain was killing British pilots daily, and the carburetor problem was contributing to those deaths. The urgency of the tactical situation created willingness to try unconventional solutions and to accept simple fixes if they worked. The test flights that proved the restrictor's effectiveness occurred within weeks of Tilly proposing the solution, a timeline that would have been impossible under peacetime procurement and testing procedures. Wartime urgency cut through bureaucracy and allowed merit to be evaluated directly rather than filtered through layers of process. Fourth, the story revealed the importance of diverse perspectives in engineering and problem-solving. Tilly approached the carburetor problem differently than her male colleagues, partly because her career experience had taught her that unconventional approaches and pragmatic solutions were sometimes necessary when conventional paths were blocked by discrimination or bureaucracy. Her experience as a woman in engineering, while creating barriers she had to overcome, also gave her perspective that her male colleagues lacked. She was accustomed to finding simple solutions to complex problems because she had spent her career working around obstacles that men did not face. This perspective allowed her to see the restrictor solution that others had overlooked, not because she was smarter, but because she thought differently. Beatrice Tilly Shilling's life and career extended far beyond the restrictor that made her famous. She was born March 1909 in Waterlooville, Hampshire, to working-class parents who encouraged her education despite financial constraints and despite cultural expectations that girls should focus on domestic skills rather than academic achievement. Tilly showed early aptitude for mathematics and mechanics, interests that were considered unusual for girls in Edwardian England. She attended local schools where teachers recognized her abilities and encouraged her to pursue advanced education. At age 18, she enrolled at Manchester University to study electrical engineering, one of only a handful of women studying engineering at any British university during that era. Her years at Manchester were marked by constant reminders that she was an outsider in a male domain. Professors made comments about women's unsuitability for engineering. Male students treated her as novelty or as threat, depending on their personalities. She was excluded from study groups and social activities that were important for forming professional networks. She faced skepticism about her abilities that required her to prove herself repeatedly in ways that male students did not. Tilly responded by excelling academically and by refusing to be intimidated or discouraged. She graduated in 1932 with honors in electrical engineering, an achievement that made her one of the best credentialed female engineers in Britain at a time when female engineers barely existed. Finding employment proved even more difficult than completing her degree. British engineering firms in the 1930s did not hire women engineers. The combination of gender discrimination and Depression-era economic constraints meant that engineering positions were scarce and were reserved for men who were assumed to be family breadwinners. Tilly applied for dozens of positions and received rejection after rejection, often without even receiving interviews. Firms explained that their facilities were not appropriate for women, or that their male employees would not work comfortably with a female colleague, or simply that they did not hire women as a matter of policy. Tilly persisted through determination that her education and abilities should matter more than her gender. She found work eventually with an electrical equipment manufacturer, though in a position that underutilized her training and paid less than comparable positions held by men. She continued applying for better positions and continued facing rejection. In 1936, she saw an advertisement for technical positions at the Royal Aircraft Establishment at Farnborough. The RAE, as a government research facility rather than a private company, had somewhat less rigid discrimination against women employees. Tilly applied, was interviewed, and was hired as a scientific officer, a position that finally allowed her to work as an engineer rather than as an overqualified technician. Her assignment at RAE focused on engine performance and on solving practical problems affecting operational aircraft. The work suited her combination of theoretical knowledge and practical mechanical skill. Tilly's personal life reflected the same determination and unconventionality that characterized her professional life. She rode motorcycles when few women did, competing in trials and races against male riders. She married George Naylor in 1938, a fellow engineer who supported her career ambitions rather than expecting her to abandon engineering for domestic life, as was conventional. They maintained a partnership marriage that was unusual for the era, with both pursuing careers and both sharing domestic responsibilities. Tilly continued working throughout World War II, despite social pressure for married women to focus on home rather than career. Her work on the Merlin carburetor problem was one of many projects she handled during the war years. She also worked on engine performance optimization, on cooling system improvements, on propeller efficiency, and on dozens of other technical problems that affected RAF aircraft performance. The restrictor became her most famous contribution because its impact was so visible and because pilots adopted the Miss Shilling's Orifice nickname. But her broader work touched nearly every aspect of RAF engine technology during the critical war years. After the war, Tilly continued working at RA through the transition to jet engines and then to rocket propulsion. She became one of Britain's leading experts on jet engine performance and contributed to development of engines for aircraft, including the English Electric Lightning Interceptor. She continued racing motorcycles into the 1950s, competing successfully in events including the International 6 Days Trial. The recognition Tilly received for her wartime contributions was mixed and reflected the era's continued ambivalence about women in engineering. She received the OBE, Order of the British Empire, in 1948 for her wartime technical contributions. The award recognized her work, but the delay between her contributions in 1940 and the recognition in 1948 suggested that bureaucratic processes were slow to acknowledge women's achievements. She was not promoted to positions of authority commensurate with her abilities and contributions. Male engineers with less impressive achievements received positions and recognition that Tilly did not, despite her demonstrated ability. She remained a working engineer rather than advancing to management or policy positions where she could have influenced broader technical directions. This reflected the glass ceiling that limited women's advancement even in fields where their technical contributions were acknowledged. Tilly apparently did not seek publicity or recognition beyond what was necessary to do her work effectively. She gave few interviews and wrote no memoirs. She preferred to work on technical problems rather than to discuss her role or her experiences. This made her contributions less visible to historians and to the public than contributions by men who were more willing to promote their own achievements. The result was that Tilly's story remained largely unknown for decades after the war, despite the restrictor's importance and despite her broader contributions to British aviation. Modern recognition of Tilly Shilling's achievements emerged gradually as historians studying World War II technology discovered her role, and as interest in women's wartime contributions increased during late 20th century. Books and articles about the Battle of Britain began mentioning the restrictor and its inventor. Engineering history publications recognized Tilly as example of women's contributions to wartime technology development. Feminist historians highlighted her story as demonstration of how women's technical abilities had been undervalued and how women had contributed to war efforts in ways that conventional narratives overlooked. By early 21st century, Tilly Shilling was recognized in Britain as one of the most important engineers of World War II, someone whose simple solution had saved pilots' lives and had affected battle outcomes during Britain's most desperate hours. The restrictor itself became artifact in aviation museums and in displays about Battle of Britain technology. Examples of the simple brass discs are exhibited alongside Spitfires and Hurricanes, demonstrating how a part that cost pennies to produce and took minutes to install made the difference between engine failure and continued power during combat maneuvers. Educational materials about aviation engineering frequently cite Miss Shilling's Orifice as example of how simple solutions can solve complex problems when someone thinks creatively and pragmatically, rather than assuming that sophisticated problems require sophisticated solutions. The restrictor's technical legacy extended beyond its immediate wartime application. It demonstrated principles that influenced subsequent engineering practice regarding expedient solutions during crisis situations. Military organizations began to recognize that comprehensive optimal solutions, while desirable, sometimes arrive too late to affect urgent operational problems. The concept of fielding good enough interim solutions while continuing development of better long-term solutions became standard practice in military technology development. The restrictor also influenced how engineers thought about fuel system design for aircraft engines. The negative G problem that afflicted Merlin carburetors was not unique to that engine. Many piston aircraft engines using float carburetors experienced similar problems. Engineers working on subsequent engine designs incorporated restrictions, anti-slosh baffles, and other features to prevent fuel flooding during negative G maneuvers. The transition to fuel injection for high-performance aircraft engines was partly motivated by the carburetor limitations that the restrictor addressed imperfectly. Jet engines, which became standard for military aircraft after World War II, did not suffer from negative G fuel problems because their fuel systems used high-pressure pumps rather than gravity-dependent carburetors. But the lessons learned from the Merlin carburetor problem influenced how engineers approached fuel system design for all types of engines. The human story behind Miss Shilling's Orifice resonates beyond its technical and military significance. It is a story about someone who refused to accept that her gender should limit her opportunities or her contributions. Tilly Shilling faced discrimination throughout her education and career, but persisted through combination of ability and determination that would not accept defeat. She proved repeatedly that women could contribute to engineering fields traditionally dominated by men, not as tokens or novelties, but as professionals whose work met or exceeded standards set by male colleagues. Her story demonstrates how discrimination costs society by creating barriers that prevent talented people from contributing fully. How many other potential Tilly Shillings never received opportunities to develop their abilities because cultural expectations and institutional discrimination blocked their paths? How many problems went unsolved or were solved less effectively because diverse perspectives were excluded from engineering and technical fields? These questions extend beyond historical interest to contemporary relevance as societies continue to grapple with how to ensure that talent and ability, rather than gender, race, or other irrelevant characteristics, determine who gets opportunities to contribute. The story also demonstrates how wartime crisis can create opportunities that peacetime society denies. Tilly Shilling might never have received opportunities to solve critical technical problems if Britain had not been fighting for survival in 1940. The desperate circumstances of the Battle of Britain created willingness to listen to unconventional voices and to try unconventional solutions. Women were allowed into roles and given responsibilities during wartime that they would have been denied during peace. The irony is that these opportunities existed because men were away fighting or because wartime production demands exceeded what male workforce could provide, not because society suddenly recognized women's abilities. When wars ended, many women who had proven their capabilities during wartime were pushed back into domestic roles as men returned and as society attempted to restore peacetime normalcy. Tilly Shilling was more fortunate than many because her civil service position at RAE provided some protection against the post-war reassertion of peacetime gender roles. But even she faced limitations and discrimination that prevented her from achieving positions and recognition commensurate with her abilities and contributions. The Battle of Britain mythology in British culture celebrates the pilots who flew Spitfires and Hurricanes, the men who fought in the skies over southern England during summer and fall of 1940. The celebration is deserved. Those pilots demonstrated extraordinary courage and skill under conditions of brutal stress. They fought against numerical superiority, and they won battles that determined whether Britain would survive as independent nation. But the mythology often overlooks the engineers, scientists, factory workers, and others whose contributions made the pilots' courage and skill effective. Aircraft do not fly themselves. Engines do not maintain themselves. Technical problems do not solve themselves. Behind every pilot who flew a Spitfire or Hurricane were thousands of people whose work made those flights possible. Tilly Shilling was one of those thousands, someone whose name does not appear in most Battle of Britain histories, but whose contribution directly affected combat outcomes. The restrictor she designed allowed pilots to fight more effectively by eliminating the engine failures that had plagued them throughout the battle's early phases. How many pilots survived because their engines did not quit during negative G maneuvers after the restrictor was installed? How many German aircraft were destroyed because British pilots could pursue them through dives without losing power? How many tactical situations were resolved in Britain's favor because the restrictor eliminated German fighters' dive advantage? These questions cannot be answered precisely, but the qualitative effect is undeniable. Miss Shilling's Orifice made RAF fighters more effective. More effective fighters meant better outcomes in combat. Better combat outcomes contributed to RAF's ultimate success in the Battle of Britain. The contribution was significant, even though Tilly's name does not appear in the battle's conventional narratives. The restrictor's story also illustrates the difference between technological sophistication and practical effectiveness. The restrictor was not sophisticated. It was a brass disc with a hole drilled through it, something that could be manufactured in any machine shop and installed by any competent mechanic. The fuel injection systems that eventually replaced float carburetors in high-performance engines were far more sophisticated, involving precision-manufactured pumps, computer-controlled fuel metering, and complex sensors. But in October 1940, the sophisticated solution did not exist in operational form, while the simple solution could be implemented immediately. The simple solution saved lives and affected battles, while engineers continued developing the sophisticated solution. Modern engineering culture sometimes forgets this lesson, assuming that sophisticated problems always require sophisticated solutions, and that simple solutions must be inadequate because they are simple. The restrictor demonstrates that simple solutions can be optimal when time and resources are limited, when good enough is better than perfect eventually, when pragmatic problem-solving is more valuable than theoretical elegance. These principles remain relevant in contemporary technology development, where the pressure to create sophisticated solutions sometimes prevents consideration of simple approaches that would work adequately. Tilly Shilling died in 1990 at age 81, having lived long enough to see her wartime contributions recognized and celebrated by aviation historians and by British society more broadly. Her obituaries described her as the woman engineer who saved RAF fighters during Battle of Britain, a characterization that, while somewhat simplified, captured the essential truth of her most famous contribution. She was remembered by colleagues as someone who combined technical brilliance with practical mechanical skill, someone who could both calculate fuel flow dynamics and personally fabricate and install the hardware needed to test her calculations. She was remembered as pioneer who opened doors for women in engineering through her example and her persistence. She was remembered as motorcycle racer whose competitive success demonstrated that women could compete successfully in fields traditionally dominated by men when given fair opportunity. The simple brass disc with precisely drilled hole that Tilly designed in 1940 changed the course of aerial combat during World War II's most critical battle. It demonstrated that innovation does not always require sophisticated technology or massive resources. Sometimes innovation requires creative thinking, willingness to challenge conventional assumptions, and courage to propose simple solutions when complex solutions seem inadequate. Miss Shilling's Orifice represents these principles in physical form, a reminder that engineering genius can manifest in simple elegance as well as in sophisticated complexity. The restrictor also represents the contributions of thousands of women who worked in technical fields during World War II, contributions that were often overlooked or minimized by contemporary accounts and by post-war histories. These women proved their abilities during wartime emergency only to face renewed discrimination when peace returned. Their stories, like Tilly Shilling's story, deserve recognition not as interesting footnotes, but as essential elements of understanding how wars were won and how technology developed. The brass discs that saved pilots' lives during 1940 and 1941 seem insignificant compared to the sophisticated technology that surrounds modern military aviation. But those simple discs represent principles and lessons that remain permanently relevant. Simple solutions can solve complex problems. Diverse perspectives improve problem-solving. Pragmatic approaches that work immediately are sometimes better than optimal approaches that work eventually. Individual creativity and determination can achieve results that large organizations and established procedures cannot. These lessons, embodied in Miss Shilling's Orifice, constitute Tilly Shilling's lasting legacy beyond the technical contribution she made during Britain's desperate hours. The restrictor remained in operational use longer than its inventors expected, because comprehensive solutions took years to develop, test, and field. The improved carburetors that eventually solved negative G problems through better engineering did not reach all operational aircraft until 1943. For nearly 3 years, Miss Shilling's simple expedient was the solution that kept Merlin engines running through combat maneuvers. Even after improved carburetors were introduced, many aircraft retained the restrictors because they added an extra margin of safety and because removing them required work that provided no operational benefit. Some aircraft flew throughout the war, with both Miss Shilling's Orifice and the improved carburetors, a redundancy that hurt nothing and provided additional assurance against fuel system problems. The restrictor's simplicity meant that it was also adopted for other applications beyond Merlin engines. Other British aircraft engines using float carburetors experienced similar negative G problems and were fitted with restrictors based on Tilly's design. American aircraft engines, some of which used similar carburetor designs, were analyzed for negative G vulnerability and were fitted with restrictors when problems were identified. The simple solution spread across multiple engine types and multiple air forces because it worked and because it could be implemented quickly and cheaply. The technical principle underlying the restrictor, that restricting flow can prevent flooding under negative pressure conditions, found applications beyond aircraft engines. Fuel systems in racing cars, fuel systems in marine engines, hydraulic systems in various applications, all adopted similar restrictors to prevent flooding or surge conditions under varying pressure loads. The principle was not original to Tilly, but her application of it to solve the Merlin carburetor problem demonstrated its utility in ways that influenced subsequent engineering across multiple fields. This is how innovation often spreads. A solution developed for one specific problem reveals principles that are applicable to many other problems. The people who develop and apply those principles in new contexts are innovating even when the underlying principle is not original. Tilly Shilling innovated by recognizing that a simple restrictor could solve the Merlin carburetor problem quickly, when comprehensive redesign would take years. Other engineers innovated by recognizing that similar restrictors could solve analogous problems in other systems. The story of Miss Shilling's Orifice, when taught in engineering schools and in technology history courses, serves multiple educational purposes. It teaches technical lessons about fuel systems and about negative G effects on fluid behavior. It teaches lessons about expedient problem solving and about when simple solutions are preferable to complex solutions. It teaches lessons about innovation and about how diverse perspectives can improve technical problem solving. It teaches lessons about gender and discrimination and about how societies can benefit by removing barriers that prevent talented people from contributing. These lessons remain relevant decades after the restrictor's operational use ended, which is why Tilly Shilling's story continues to be told, and why the simple brass disc she designed remains significant beyond its immediate wartime application. The mythology surrounding Miss Shilling's Orifice has grown over decades since the war. Some accounts exaggerate the restrictor's importance, suggesting that it single-handedly won the Battle of Britain, or that RAF would have lost without it. These exaggerations are understandable because the restrictor makes for compelling story, but they are not supported by evidence. The Battle of Britain was won through combination of factors including pilot skill and courage, radar-directed interception, numerical strength despite German advantages, German strategic errors, and British industrial mobilization. The restrictor contributed by eliminating one tactical disadvantage that British fighters had faced, but it was one contribution among many that collectively determined the battle's outcome. Other accounts minimize the restrictor's importance, suggesting that its effect was marginal and that the carburetor problem was relatively minor inconvenience rather than serious tactical limitation. These accounts are also not supported by evidence. Pilot testimonies consistently emphasized how frustrating and dangerous it was to have engines quit during combat maneuvers. German pilots explicitly recognized and exploited British fighters' inability to dive without losing power. The elimination of this problem was not marginal. It was significant tactical improvement that affected combat outcomes. The truth lies between exaggeration and minimization. Miss Shilling's Orifice was an important contribution that improved RAF fighter effectiveness during critical period. It was not decisive by itself, but it was a significant component of the larger effort that allowed Britain to prevail during the Battle of Britain and to continue fighting through 1941 and beyond. Tilly Shilling's career after the restrictor's success continued to be productive, though never as publicly visible as her most famous contribution. She worked on jet engine development during the late 1940s and 1950s, contributing to Britain's transition from piston engines to jet propulsion. She worked on rocket engines and on early guided missile propulsion systems during the 1950s as Britain developed its deterrent capabilities. She continued racing motorcycles into her 50s, competing in trials and endurance events and winning trophies that demonstrated her mechanical skill and physical endurance. She retired from RAE in the early 1970s after more than 35 years of service, having witnessed British aviation technology evolve from biplane fighters to supersonic jets to space launch vehicles. Her retirement was spent in relative privacy, gardening and maintaining her home, and occasionally corresponding with aviation historians who contacted her about her wartime work. She died November 1990. Her death noted in engineering publications and in aviation history journals, but not widely reported in mainstream media. The recognition she received posthumously exceeded what she had received during her life, as historians and biographers discovered her story, and as her contributions were celebrated as part of broader recognition of women's wartime technical work. Streets and buildings were named in her honor. Scholarships for women studying engineering were established in her name. Exhibits about Battle of Britain technology featured her story and the restrictor she designed. The simple solution she conceived during desperate circumstances became symbol of innovation, of perseverance, of women's contributions to victory, and of the principle that complex problems sometimes yield to simple answers when someone thinks clearly and pragmatically about what needs to be accomplished. The brass disc with the precisely drilled hole, Miss Shilling's Orifice, represents all of this. It represents technical ingenuity applied to urgent operational problem. It represents willingness to accept good enough when perfect is unattainable. It represents how one person's creativity can affect outcomes of battles and wars. It represents how discrimination and cultural barriers prevent societies from benefiting from talents and abilities of people who do not fit conventional expectations. It represents the thousands of unglamorous contributions by unnamed engineers and scientists and technicians whose work made possible the heroic actions that history celebrates. The restrictor in Aviation Museum display case looks insignificant. It is a small brass disc, unremarkable in appearance, simple in construction, the kind of part that visitors might walk past without noticing. But that simple part saved pilots' lives during Britain's most desperate hours by solving a problem that more sophisticated engineers had been unable to fix quickly enough to matter. That simple part embodies principles and lessons that transcend its specific application and that remain relevant to how we think about innovation, problem-solving, gender, opportunity, and what matters when survival depends on making things work rather than on making them perfect. Tilly Shilling understood what mattered. She designed something that worked, that could be implemented immediately, that solved the problem pilots were dying from every day. She did not wait for perfect solution. She created good enough solution, and she delivered it when it was needed. That is what engineering is supposed to do. That is what Tilly Shilling did. And that is why her story and her simple brass restrictor deserve to be remembered and celebrated as essential contributions to victory in World War II and as examples of what individuals can accomplish when creativity, determination, and practical skill combine to solve problems that matter.